Jochen, if you're happy that we proceed, just give me a nod.
Yes, can you hear me?
Yeah.
Okay. Yeah, maybe a few words. So I think we're very fortunate to have sort of a bit of an interdisciplinary TYC online meeting today with a real condensed phase quantum theorist, Andrew Green, and so he will talk about different approaches to doing computational condensed matter physics, and so not only the way we're used to do it, like with computers and high performance computing, but also with real sort of theory. And I think Andrew will basically try to explain, how these two things can work together. And then the second talk is Ben Slater, and he will talk about some materials modeling of porous materials. And so after the first talk, I will chair the first session where everyone can ask questions. So you're all, very welcome to ask questions after each talk. All right. So Andrew, please, if you would like to start.
Great. Thanks very much, Jochen, and thank you very much for the invitation to talk today. Let me just try and get my slides sorted out first of all. So yes, thanks for giving me the chance to tell you a little bit about the work that's going on in my group today. The way I understood the chance to talk today was a chance to share the approaches and techniques and so on that we're using in our group, and because perhaps many of you in the TYC I don't know personally, and it would be good to make that introduction. So one of the things that I've found in my career so far is that, there are lots of tools that we use in condensed matter theory and numerical condensed matter, and they're very mature. And often the groups of people who are using them interact with other people who use the same tools, and they've almost separated into subdisciplines. But I actually think that that's changing. And I'm going to tell you about 2 projects, maybe 3 projects, depending on how much time I have, that my group is involved in, that really involve some sort of interaction across these sort of subdisciplines. So here are some of the people. These are people in my group: Jamie, Adam, Vinod, PhD students at UCL, and Fergus and Lewis are PhD students at KCL. And here are some of the people that I've been collaborating with in the work that I'll tell you about. In particular here, the name Chris Picard, I'm sure is well known to many of you, and James Commode probably as well. Chris and I have been good friends for many, many years, and actually I'm pleased to say finally in the last couple of years we've actually started collaborating on some physics. Prior to that, it had been just fly fishing that we collaborated on. So let me give you a bit of an outline of what I'm going to talk about. So the first project, let me use this annotation tool. So this first project is really about attempts to incorporate some techniques from sort of analytical condensed matter physics into density functional theory. And so I'll give you a little overview of that, but the basic idea is that there are some tools we have for describing fluctuation-induced phases, so new phases of matter induced by quantum fluctuations of the electrons themselves. And the story when I was learning condensed matter physics was that, oh, these techniques you need field theory for these techniques you can use numerics for. But actually a lot of advances in both numerics and theory are allowing those barriers to be broken down. And this is our attempt at doing that, attempt at addressing some of those barriers. The second one is about the use of tensor network techniques. So these are classical numerical techniques for dealing with predominantly with spin systems. But recently we've been using them to, or transporting those techniques to quantum computers. And I'll tell you about some results we have there. And also over this time, I may, for some reason my thing is not advancing now. What's going on? I can't actually see my mouse and I can't advance. Ah, there we go. So then beyond that, why are my slides not advancing? Maybe I need to go to the bottom. So beyond that, I may tell you a little bit about using tensor networks in quantum machine learning. Okay, so to this first part, this idea of fluctuation-induced phases and how we might incorporate them into density functional theory. So the idea of spin fluctuations inducing pairing really started in the study of helium-3 and the superfluidity in helium-3, how that might arise. And it goes back as far as 1960s and 70s, where the idea was that the fluctuation, the spin fluctuations on the face of it are repulsive. But when you allow for the fact that they're retarded, so they take a certain time to propagate, you can get an attractive interaction. And diagrammatically, that's summarized by saying that if you take these spin fluctuations exchanged by pairs of electrons, you can actually generate an interaction between the electrons that leads to pairing. And this, this captures the idea of superfluidity in helium-3. And it was also used by Fay and Apel in the 80s. It was applied to metals, to the potential for spin fluctuation-induced pairing of electrons to give superconductivity. So this is an important technique, and essentially whenever you read about a spin fluctuation-induced pairing mechanism, this is the calculation that's done. So it's what the calculations that were initially done for the pnictides. There were sort of electronic structure calculations that were followed by people using the results of those calculations in spin fluctuation calculations to try and predict the pairing mechanism and the pairing channel. But it doesn't capture all instabilities, particularly in ferromagnets. And this is really where my group came in. So these are ferromagnets you can think of as pairing in the particle-particle as opposed to the particle-hole channel. And my group, together with Frank Kruger and initially with Ben Simons and Gareth Conduit in Cambridge, we developed this idea, an alternative perspective on this type of how the electronic fluctuations could lead to ordering. And the idea is really illustrated by this little diagram here. So if we introduce some order into a Fermi liquid, this corresponds to some deformation of the Fermi surface. And that modifies the dispersion of the low-lying particle-hole excitations. And in fact, certain distortions can lower the fluctuation-free energy of those particle-hole fluctuations. Well, this in turn will favor the order, and you can see you get a feedback between the two, and this mechanism can lead to new types of order in the system. You have to self-consistently determine the ground state in this way, but if you do this, it leads to a unified picture of fluctuation-induced order. So one can understand it diagrammatically as a resummation of all of these diagrams in the conventional diagrammatic approach. But one of the nice things is that it allows us to talk about instabilities like superconductivity at the same time as instabilities such as helimagnetic instabilities entirely induced by fluctuations as opposed to being induced by spin orbit terms and so on. So we developed these approaches over a number of years. Okay, so we've applied them to quite a number of different systems. So here is applied to a model of ferromagnetism. So this is basically the Stoner model of ferromagnetism. And if you don't do anything, you find you get a continuous transition that you can tune to 0 temperature. If you allow for certain helimagnetic instabilities, you find that you get a spiral phase. If you allow for the instabilities in the superconducting channels, you get an interplay of superconductivity and ferromagnetism, a p-wave superconductivity, and potentially an overlap of the helimagnetism with the superconductivity. Some of these effects have been seen in experiments. We've used this essential idea to understand the anomalous phase in the helimagnet MNSI, and we've made other predictions along the way. So we can use this approach to essentially any problem, any situation where you have an order that's induced by electronic fluctuations, you can understand with this sort of mechanism. So here are a few details. The essence of what we do is we identify some order parameters. So we guess that there might be some particular type of order in our system, maybe superconductivity, maybe helimagnetic order, or whatever. And we introduce a conjugate field to that order. Typically, these the operator that creates the order, or whose expectation is the order parameter, will be something bilinear in the electrons. And if we add that to our Hamiltonian, we can work out the partition function or the generating function in the presence of that order. We diagonalize the quadratic parts and treat the rest with, in some way, either diagrammatically or some such, to get the effect of the fluctuations. So there's actually an alternative, simpler way. In the case of the ferromagnet, you can formulate this as follows. So this first line here is essentially the free electrons, the free energy for free electrons in some ordered background. And here I'm illustrating in the case of magnetic order, but basically this dispersion is the dispersion of electrons in some magnetic background or some ordered background. And then you can calculate the rest of the free energy by calculating fluctuation corrections perturbatively. And this is just the second order perturbative contribution where you're calculated in the background of whatever the order parameter is that you're looking for. And already this reproduces a lot of the results that you get from the diagrammatic calculations. So the fact that this second order perturbation theory is carried out self-consistently in this mean field background effectively resums infinite sequences of diagrams that you would have in the diagrammatic approach. One could do the same for the superconductor. And in the case of the superconductor, because this is an anomalous order, one has to work a little bit harder. And we introduced a trick where we were able to add and subtract this term, which couples the electrons to a superconducting order parameter, and then treat this first line. We just diagonalize this first line with a Bogolubov transformation and treat the rest in second order perturbation theory. And this gives you a rather neat derivation of a free energy function for the superconductor that reproduces spin fluctuation theory, and at the same time allows us to work, include both the magnetic order and spatially modulated magnetism at the same time as the superconductivity. So this work has been developed in quite a number of papers, but one where a lot of the details of formulating and computing these rather nasty integrals was carried out by Una Karasanovic and Frank Kruger. This was while we were up in St. Andrews. And the superconducting result was in a paper with Gareth Conduit and Chris Bedder. So we were very pleased with this reformulation, although actually we realized sometime later that Kleinert had come up with this trick essentially. He introduced it as a variational approach to superconductivity, but it's essentially the same thing. We were not aware of this. Actually, when we first encountered Kleinert's paper, we wondered why he had referenced our work. And if you look at the years, this explains why he hadn't referenced ours. Now we wonder why we hadn't referenced him. It's because we didn't know about his paper. And the structure of this general theory on the left-hand side has strong similarities with density functional theory. And that's really why I thought it would be an interesting thing to tell you about today. And it really brings me to the point of this talk. In fact, this approach to the superconductivity, we suspected was rather similar to the approach to superconductivity introduced by Hardy-Gross. So I'm in particular in 2014, there was a paper out of Hardy-Gross's group where they dealt with electronic fluctuation-induced superconductivity. And this is really doing essentially the same thing as we're intending. So there's strong similarities with superconducting density functional theory. But of course, this approach can be applied in general if you think there's some sort of novel order likely in your system. In principle, you can do a calculation of this type and check whether it works. Now, to date, the way in which that has been done is the analytical theorists like myself will ask their numerical colleagues to come up with the electronic structure, and then we'll use some of the detail from that to do the fluctuation calculation. But really, we ought to be able to do them at the same time. And this is a project that Adam Walker, my PhD student, has been working on for the last couple of years. The basic idea is that this quantum order by disorder approach can allow us to augment the energy functionals, the exchange correlation functions, exchange correlation functionals that you have in density functional theory. If we posit a certain type of order, this gives us a framework to say how we should modify the exchange correlation functional in order to accommodate that order. So Chris Picard and James Commode have been advising Adam on how to get into the workings of CASTEP, in fact, using CAS-PyTEP, and Adam has been able to calculate the modifications to the exchange correlation functionals that are due to this quantum order by disorder effect. His next task is really to point those into the density functional loop so that we can, let's say the superconducting order parameter, for example, can be optimized at the same time as the density itself. Okay, so that's the first part of my talk. The next bit was about including tensor networks on quantum computers. And so let me begin by saying a few words about tensor networks. I'm not sure how familiar they are in the TYC, but the essential idea, Hilbert space for many body systems is enormous, and tensor networks exploit the entanglement structure of wave functions to find efficient classical representations. So for 1D spin systems, this is basically the tool. Nothing beats DMRG in 1D. In 2D, there are approaches like PEPs, which stands for projected entangled per states, that are competitive with other techniques. But let's say the dominance of DMRG in 1D is not quite matched in 2D. So why would we want to translate these algorithms to quantum computers? Well, because these algorithms are state of the art for classical simulation of spins, you might hope that we can use some of that to come up with state-of-the-art quantum algorithms. But there's an argument that says that perhaps the quantum computer is actually the natural home for these algorithms. And I'll say a little more about that in a moment. And by focusing on the entanglement structure of these states, we have some hope that we can get a quantum advantage in our computations. So these figures at the bottom, for those who are familiar with tensor networks and tensor network algorithms, you'll realize that in a tensor network algorithm, typically, so I'm thinking about matrix product state. So this will be a matrix product state of these dangling legs at the bottom here would describe spins. And these legs inside this chain are auxiliary indices that we sum over. And in a tensor network algorithm, every step of the algorithm involves returning these tensors to a form that's actually an isometry that says that these can be re-expressed in a way that they form some subset of the elements of a unitary matrix. And actually, most of the time in a classical computation involves returning your tensors to this canonical form. Now, if you implement these matrix product states on a quantum computer, actually, you are automatically in canonical form. You don't have to do this recanonicalization at each step. So this actually gives the impression that perhaps this is the natural home for these algorithms, and that's really what I meant by this comment here. So we have a paper on the archive where we show how to do this. We've given it a fancy name, parallel quantum simulation of large systems on small quantum computers. The idea is that actually the algorithm we demonstrate in this paper simulates an infinite system on a finite quantum computer. In principle, we can simulate any system that's larger than our quantum computer on our small quantum computer. given the techniques that we've developed. So this is a quantum circuit representation of the matrix product state. And formally, if it was a translation invariant state, this would end up being an infinitely wide and infinitely deep circuit. But using the tricks of tensor networks, we can write any local observable in terms of a finite circuit. And the basic idea is that this tensor V here is implied by the tensors U that describe the state, and it tells you what is the effect of the rest of the system far away from where you're making your observation. And we've been able to show how to implement these algorithms on a quantum computer. So let me see what my next slide is. So these are the actual circuits you have to implement. Where does the quantum advantage come in here? Well, this is really an area that's, let's say, at the edge of our understanding at present. But the notion is that there's some entanglement and complexity are somehow different. So in particular, typically when you simulate the time evolution of a spin system, you find that the entanglement will grow linearly in time. And in order to capture that with a matrix product state simulation, you need a bond order. So the size of the matrices or the size of the tensors that form this tensor network description grows exponentially in time. And really, that's the fundamental barrier for how long you can integrate your time evolution of quantum systems. But it turns out you can actually do better. That really the complexity of these states only grows linearly in time. There are various quantum information proofs of this, and at the very least, one is that you can trotterize a time evolution, and that suggests that the number of parameters you need to describe the system is only growing linearly in time. One of the interesting things here is that so we can come up with a factorization of our unitaries for our algorithms that takes advantage of this complexity window. So we can find states that have got high entanglement but only need a few parameters to describe them. The interesting thing is, although we can write down those states with a few parameters, it turns out that the time it would take you to compute the properties of those states classically is still has this exponential scaling, but on a quantum computer you can do better. So we demonstrated, well, in collaboration with Frank Pohlmann's group in Munich, we demonstrated that this particular subclass of matrix product states has this property that allows you to simulate within this complexity window. And we've also been able to demonstrate this on IBM's computer to demonstrate that we can use these translationally invariant matrix product states realized on a finite quantum computer, and we can demonstrate a topological phase transition on those systems. Actually, we believe in this paper it was the first demonstration of any phase transition on a quantum computer, because of course a phase transition strictly requires you to work in the thermodynamic limit. Okay, I'm going to wind up relatively quickly here. I see we're supposed to finish at 25 past to give time for questions. So the thing we're most proud of, I think, is that we can optimize these states. And this is indeed what most works on using quantum computers for quantum chemistry or condensed matter physics have focused on optimizing states to describe a Hamiltonian. But in fact, we've been able to time evolve these states and come up with a particularly efficient representation of the time-dependent variational principle. And the reason this is so efficient, in fact, is that the unitaries that represent the state actually also encode the tangent space to the point on the variational manifold that you're describing, that describes the state at any particular point in time. And realizing that allowed us to come up with a particularly simple realization of the time-dependent variational principle. We've run this code in simulation. The code is available on a GitHub here that's hosted by Fergus Barrett, and it's listed in our paper online. But we're currently working with partners at Google to hopefully run this code on their computer in the not too distant future. And we have various ways in which we're taking this forward in order, first of all, simplifying our algorithms so that they can run on computers that aren't quite as good as Google's computer. And then this actually allows us a way of approaching two-dimensional simulations that are rather simpler than the general PEPS simulations we might hope to do. And so this is something we hope to have working in, this bit is already working actually. We hope to have this genuinely 2D simulation working probably early in the new year. I'm going to take 1 minute. In my group, we've begun to think about using quantum computers for image classification for, let's say, machine learning tasks. And in fact, our focus has been the following, is to recognize that learning is a dynamical process. So training a classifier is a dynamical process in itself. And our hope is that we can take insights from quantum statistical mechanics to improve our algorithms for that. So for example, we know from statistical mechanics that the thermal state that we end up in as a result of coupling to a larger system is largely independent of the details of that larger system and indeed of our coupling to it. And the hope is we could harness that robustness to make more robust quantum information algorithms. And we have a preprint that we put out just a couple of weeks ago where we came up with an alternative algorithm for doing something called amplitude amplification. The idea is you do some computation, which is you're trying to come up with some part of your wave function that solves a problem of interest. And you have a bit of the wave function that's incorrect. And amplitude amplification essentially enhances the amplitude for the bit that you're interested in. And we've come up with a way of doing this inspired by eigenstate thermalization that is more robust to gate noise than the techniques that preceded it. And this graph here actually has data that has some simulated data and has data that we collected on one of IBM's machines. Okay, I think with that, I'll finish and see if there are any questions. Oh, I should mention another name that will be familiar to those of you from King's particularly, but I guess all of you in the TYC is George Booth, who is actually Lewis Wright's supervisor in King's, and together we've worked on this idea of, well, that we're calling ancilla thermalization for a robust way of doing amplitude amplification. Questions?
Thank you very much, Andrew. Very nice overview talk. That's exactly according to sort of our protocol, our discussion that we had before. Please, if anyone would like to ask a question, please do it now before we start with Ben's talk. Are there any questions? Is Karen still around? Not sure. I have
no idea.
I think. Yeah. Is there anyone? I can't see.
Nothing's up in the.
Should I?
Oh.
Let me stop sharing my screen so that will enable Ben to come in when he needs to, and then I can actually see if anyone has a hand raised as well. No hands.
I don't see anyone raising their hand.
Well, thanks very much for
so maybe I just ask a question. Could you very quickly say a little bit more about how you actually try to modify this exchange correlation functional to reproduce these electronic fluctuations? So that was a bit too fast for me. There was this slide on the right-hand side.
Okay, let me share again. Let me go back through my slides. There was a RevMod Phys about dynamical mean field theory by Gabby Kotliar and others, probably about a decade ago now. But he did a very nice job of putting density functional theory and dynamical mean field theory in a sort of unified framework, and actually, you know, that's the essence of how these different techniques relate to one another. But the idea in essence is that you have your well, actually the essence is very similar to the essence of Hardy Gross's work. So you as well as having a your Cohn-Sham equations are supplemented by, as well as having a charge density, you have a superconducting density. And in Hardy-Gross's approach, you have this is a function that may have different values at all points in space. It is actually a function. In our approach, we choose a particular order parameter, and we just optimize that one number. And actually, although that's reducing, in principle, reducing the number of states we can describe, it makes it easier to optimize and easier to address the state that we're looking for. So this gap equation, you can view this as the first differential with respect to delta of some free energy function. And in fact, the nonlinearity of these equations is that this dispersion here is the dispersion in the background of the superconducting order. And actually, when you're calculating these Cohn-Sham equations, in fact, you have to allow for that modified electron density that comes out from having this dispersion modified by the superconducting order parameter. Mm-hmm. So it's really, you have this additional equation to solve. In our case, you have this additional equation to solve. You have to optimize this delta, and then you have this additional equation to solve self-consistently for the Cohn-Sham equations. In Hardy-Gross's work, you have not just a single equation, it's a functional equation that you have to solve for a superconducting density function. But here it's just a superconductor. Well, I mean, I've got a momentum dependence, but typically we investigate whether there's superconductivity in a particular channel, just to simplify these equations. Does that answer the question?
Yeah, thank you. I got a little bit of a better idea. Thank you very much. Just wondering if nobody else is asking question. We just thank you, Andrew, again for a very nice talk.
Okay, thanks very much, Jochen.
And we continue with Ben.
Can you see this?
Yes, Ben. I think Ben is very well known to us, of course, in TYC community, and he will talk about optimization, characterization of nanoporous materials. Ben, please.
Just let me see myself. It's rather unnerving. I can't actually see myself. But anyway, we've just heard a very nice fundamental talk, and I'm going to be giving actually a highly applied kind of materials chemistry talk. I'm going to be talking about our work, which is chiefly examines nanoporous materials. And I'll present one kind of finished story and some work in progress. So we work on actually quite a broad range of materials. Today I'm going to be talking about two classes of materials, metal organic frameworks and zeolites. I'll describe what those are shortly, but we're also quite interested in many other materials, in particular water ice, dense oxides, 2D layered materials, and so on. My particular point of interest is order disorder problems, and also surfaces and the role of defects on things like catalytic behavior, and we use a broad range of methods. So let me first start off by plugging some work on water ice. This is a review that we published in Nature Reviews Chemistry just over a year ago with Anglos, and that's all to do with essentially surface chemistry and surface structure of water ice. And more recently, another aspect, which is something that we published heavily on, is hydrogen ordering in water ice. And this is a paper that, in collaboration with my colleague Christoph Salzmann in the chemistry department, and that work has just been uploaded to ChemArchive. And here's another plug, and this is the fruit of my group's efforts over the last during lockdown, which precipitated this. So it's a very extensive review of essentially high throughput methods in synthesis, characterization, to some extent robotics, simulation, and machine learning in the optimization and identification of porous materials. This is my group here, the photos uploaded from Interpol earlier on today. I'm going to begin by talking about just one particular story to do with metal organic frameworks. So because I'm aware this is a very broad audience, I'm just going to describe very briefly what a metal organic framework is for those of you who are not familiar with that. So basically this thing over here is a well-established metal organic framework. The blue part is a metal containing cluster, and this is linked by a phenyl aromatic benzene dicarboxylate ring. And this is a family of materials, the so-called, it's an example of something called an Reticulum Moth. Nice thing about this is you can preserve the topology of the underlying material, but you can vary the functional groups in between. So that varies the chemistry, and it also varies, because you can vary the chain length, so you can vary the porosity. And the huge porosity of these materials actually recommends them to a large variety of different potential applications, including things like sequestration, separations, storage, even drug delivery. So some of the pore apertures can be in excess of 100 angstroms, so they're really very large indeed. And to give you an idea of the surface area of these materials, I think the current record holder is this cryptically named material called DUT60 from the Caskell group. That has a surface area of 7,800 square meters per gram. So that is approximately 1.5 times the surface area of a football field in 1 gram of material. So these are incredibly porous materials. They've gone from being hypothecated materials, well-studied materials, to products. This is one particular example of an actually quite a niche application of a metal organic framework, but there are issues, barriers to these materials becoming more mainstream. These are several to do with synthetic processing, scale up, cost of the reagents, and so on. The main obstacles actually now is chemical stability, thermal stability, and in particular these things defects, and that's the next story that I'm going to focus on. So this is a material called UIO66. What I want to draw your attention to are these things, which are polyoxymetallate clusters. In this case, they contain zirconium, and these are linked by this thing here, which again is a benzene dicarboxylate ring. So you can see there's two oxygen atoms there, which link to the metal, which is shown in blue. So schematically, we can think of this structure as like this, and it happens to have an SCC, face-center cubic type arrangement. So the clusters map onto these things, or the spheres rather map onto these things, and the linkers represent these benzene dicarboxylate linkers. And we published this work in collaboration with this person, Yu Han, who's a specialist in the application of transmission electron microscopy in Nature Chemistry, again, just over a year ago. And this is a specific study to actually investigate defects within this material. This particular material is super interesting because it's unlike most moths, it's water stable, and it is thermally stable. It's also mechanically stable. And rather curiously, it's a very good catalyst. And it's been established for quite some time that the efficiency of the catalyst is proportional to the concentration of defects within this material. And it turns out you can prepare this material with 40% of defects, which is really extraordinarily high. The issue is, what's the proportion of cluster versus linker defects? And specifically, do they have a particular role on facilitating catalysis? So it's been known for some time that missing linkers and missing clusters, these have been inferred from surface area measurements and XRD, but they've not been evidenced through real space approaches. So this is where our collaboration with Yu Han was instrumental. So what I want to draw your attention to is this particular figure. So this is the unit cell of UIO66, which has been rotated, so looking along a particular plane. And you can see here that along here we have flat phenol rings. And these actually map onto these struts, which you can see highlighted in this TEM measurement, or TEM image rather. Now, on investigation, it turns out that this sample also had areas like this. And here you can see that we have missing struts. So in terms of an atomic picture, we've lost those phenol rings. And these happen in an ordered way in this particular part of the crystal. And in fact, you can solve the crystal structure of this nanodomain within UIO66, and it has a particular topology, which is called BCU, and a particular symmetry. But it gets more complicated because there are other types of essentially nanophases within the structure. So one is based on what's called the REO topology after rhenium trioxide, and that's basically where you have a missing cluster. So within this image here, these blue spots are supposed to represent they're highlighting where we would expect to have these polyoxymetallate clusters. So if I draw your attention to these red bracketed regions here, so there's a kind of spot here, there's a spot here, there's a spot here, and so on, but there's no spot in the middle, and that's evidence of direct evidence of a missing cluster. And it turns out there's also missing linkers associated with that. And then there's yet another example, which has a distinct topology. Again, it's part of the same crystal. This has a distinct topology, and this is SCU, a particular, it's got missing linkers and missing clusters, but they're arranged in a different way than the REO phase. So you can see that there's an observable concentration of these defects, which suggests that they might have low formation energy. So this is where we came in, and so we've computed the respective energies of forming these different types of defects within the unit cell of perfect UIO66. So all of these energies are expressed with respect to this perfect structure. So the absolute formation energies of these defects is incredibly low. These are in kilojoules per mole. And because the energies are so low, we'd expect the concentration of these defects to be high, and that maps onto what we can actually see, because the TEM directly shows you that we have observable concentrations of these particular defects. It's a little more interesting than this, because it turns out that actually, if you look at the evolution, you can map out the pore size distribution as a function of the synthesis time. So the black and the red parts of this plot highlight that there are large pores after 1 day and 1 hour and 1 day respectively. But after 3 days, these large pores are absent, and these large pores are associated with those missing clusters. So this is telling us that actually, as the synthesis time evolves, we essentially make the crystal more perfect. It's indirect evidence of Ostwald ripening, but we actually have more direct evidence of Ostwald ripening occurring. But in particular, we have now a distinction between crystals, which we can extract earlier on in the synthesis, which have missing clusters, and those taken from later on in blue, where we have no missing clusters. So we can make a distinction between the catalytic behavior of the missing cluster type defect and the missing linker type defect. So the formation energies, defect formation energies, are actually associated with, can be used to rationalize that what we've just seen. So these SCU and REO type nanophases, these have the largest formation energy. BCU have the smallest formation energy. So we think over time, what's happening is that we're seeing an infilling of the defective material, which tends towards this perfect material. So I've just mentioned that we can make a distinction between crystals extracted early on in the synthesis, which are rich in missing linkers, and those at the beginning of the synthesis, which are rich in missing clusters. It turns out that the missing clusters are super effective catalyzers of one particular prototypical reaction, isomerization of glucose to fructose. And we don't have a direct explanation for that. That's something that we're actually looking into right now. We think potentially it's just steric constraints, and the missing clusters are so potent because there's just more open space. So it's easy for the reagents and products to get access to the active site. We're doing work to understand actually the pathway for the fructose formation. This is work of Martin Hutero, and here we can see in this little movie, which comes from ab initio MD. So this is some glucose, which is attacking a defect site within the material, and we've mapped this out using umbrella sampling. And actually, it turns out that the initial step in this process for the formation of the fructose actually has a relatively small barrier associated with it. The other thing that we've been looking at is exploring how fluxional these frameworks are. This is a formate species. What's highlighted in here is with orange is a benzene dicarboxylate group, which is linked to the polyoxymetallate center. And using metadynamics now, we can follow the decoordination of that species. And it actually turns out that these materials are much more dynamic than we anticipated. So I've talked about I've given you one specific story with reference to UIO 66. I wanted now to just present some more kind of work in progress, essentially. And this is our more developmental work, which has been inspired in part by to use high throughput techniques to identify metal organic frameworks and zeolitic systems for particular applications. So this is an image that from our paper that I mentioned earlier, this huge review. And really we're working on these areas and these areas. And what we're actually trying to do is solve essentially a materials chemistry problem using computation. There's a huge range of existing metal organic framework structures. So there's over 100,000 reported crystal structures. So which particular metal organic framework is best for a given application? And if we identify the best one, can we make it even better? So we've been developing tools to now to look at particular applications. So here's a kind of sample application, which is here what we're trying to do is identify materials which would be good for extracting methane from coal mine flue. So this is a mixture of methane, CO2, oxygen, nitrogen, and water. Each of these points here is the outcome of a RASPER Widom particle insertion calculation. And we actually have about 8,000 frameworks depicted in each of these plots. We've got selectivity here, the propensity to select for methane. And on the horizontal axis, we've got the largest cavity diameter, which is just simply as you might expect, is the largest kind of hole, but it might be something which is rather oblate. So it's largest dimension within the structure. So broadly, the the selectivity for these individual gases is rather similar. You can see for CO2, we require very small cavities within the structure in order to discriminate for the methane. You can also, we colorized the structures for the heat of absorption for methane. So you can see that selectivity is very much correlated with high heats of absorption and relatively small cavities within the structure. I can't show it now, but in fact, we have the capability to hover over each of these points and interactively identify which structures, which of the reported crystal structures these map onto. So we can quickly identify a promising structure. So that's selectivity of methane against individual components, and we can then do grand canonical Monte Carlo calculations and actually compare a real mixture of methane, CO2, and nitrogen in this proportion, and we find something which is broadly similar to what we found before. This is actually now a subset of the frameworks we were looking at before. Again, methane absorption is important, and we do require relatively small pores within our materials. So we'd obviously like to go beyond that. So Tom Pope, who did these calculations, has been using machine learning to try and identify good descriptors for this particular process. So we see here the outcome of a random forest machine learning fit. It's relatively, it's a reasonable R-squared value, and this allows us to pick out gives us some chemical insight and identify the important features which are good at, which are responsible for the high selectivity for methane. And in fact, in more recent work, which we haven't had a chance to properly analyze, is used now a neural network type approach, and this has given a much higher R-squared. And so the challenge now is to extract the features and feature importance and see whether there's any significant difference between with respect to these. Qualitatively, of course, everything makes sense. You know, here we have, you know, the most critical thing is the heat of absorption for methane. I'm now going to quickly go through our high throughput work on zeolitic systems. So zeolites are aluminosilicates, framework aluminosilicates. So these are absolutely ubiquitous in chemistry. They've been used as catalysts and separation materials for approximately 70 years in petrochemistry. It's about, unlike moths, where we have 100,000 types of structures, about 200, just over 200 structure types, of which a small fraction are actually used in industry. The issue is that for catalysis, we need to know, we want to identify a structure-activity relationship to understand what makes a good catalyst. And that boils down to, amongst other things, identifying where the aluminium is in the structure, and we can't use experiment to identify that unambiguously. And so this is why we're using simulation. And the idea is that once we identify the structure, we can say whether they can be improved upon in some way, or we might even identify some new materials. So this is high throughput in inverted commas density functional theory calculations, where we've taken one particular zeolitic structure and we've evaluated all possible unique structures for this complex framework aluminosilicate. And I'm not going to go into any great detail here. It is important to know that this is a sodium compensated structure. There's around 1,400 structures here. And I just want to pick out some particular sequences which are important. We've got relative energies here. We've got the distance between aluminium atoms within the structure. So this is one particular concentration of aluminium that we've examined here. And we can see that the lowest energy structures are associated with these types of sequences. So this is what we would call the next nearest neighbor. It's less favorable to have this type of sequence and least favorable to have these linkages here, aluminium, oxygen, aluminium. And I'd like you to try and keep hold of that thought. Now this is fine, but this costs a lot of compute time. And it turns out that the real catalytic materials are extremely complex in terms of composition, in terms of their crystallography, and in terms of their symmetry. And so we can't use brute force DFT to evaluate all of the possible configurations for some of the more industrially relevant materials. So hence we've been looking towards, again, machine learning. So this is the SOAP model, which we heard about a few weeks ago from Professor Gianni in Cambridge. And here we've taken the data, we've taken a subset of the data that I just showed you, used it as for training, and we actually produced a very good correlation now with a very modest error. So this looks rather promising. We've then used that in anger to look at something which is completely impossible to examine using brute force DFT. So here we've used a different ratio, a different proportion of aluminium, where there are 67,000, in excess of 60,000 distinct framework types or configurations, using the machine learning model developed by Dan Hewitt. It turns out on a single processor, we can evaluate all those configurations within about 3 hours. At the DFT level, we'd be looking at around about 2 billion. And we can see broadly, there's similar features to what I showed you before, but there are some extra insights which I don't really have time to go say too much more about. We're also doing, Danny's also doing high throughput work. So this is very much in parallel with Tom Pope, who are exploiting similar kind of know-how. The colorized points here are from around 20,000 hypothecated zeolitic materials, and the black triangles here are known reported zeolitic materials. And what we're measuring here is the selectivity of methanol to ethene, which is important for one particular catalytic application. Now, you can see, again, we're using this largest cavity diameter as a key descriptor, and we're interested, of course, in the selectivity here. And we can see again that the heat of absorption of methanol is an important kind of parameter. What I want to draw your attention to is that actually, and this surprises me, that there's only about 7 or 8, if we include this structure, there's only about 7 or 8 materials which beat the known frameworks. So this is perhaps a tiny bit pessimistic, and it suggests that maybe the low-hanging fruit, the already synthesized materials, are actually already doing a very, very good job, and we're going to have to work very hard to beat those. We can do a similar kind of thing in terms of machine learning and measure the feature importance. And again, this just emphasizes that the heat of absorption of methanol is absolutely crucial. I've just got 3 more slides, and I just want to just briefly describe some work by Ivan Clayson, who's looking at different types of problems in zeolites, and these are to do with transport and exchange and also segregation. I'm not going to go into this in any detail, other than to say that it's important to, often we want to incorporate different types of metals into the frameworks, and we need to understand the processes by which we can exchange those metals into the structure. So we've been using essentially simulated annealing, periodic DFT, and examining the barriers to migration within the, this is from one cage to another, so that's a rate limiting process. It turns out there's a lot of complexity here that you wouldn't perhaps anticipated. This is really quite different from, say, alkanes within these materials. not only are there large changes in the coordination number, which is shown in blue, all these different points here with triangles, crosses, diamonds, and so on, they all represent distinct point group symmetries of the metal as it traverses through these cages. And then something that I hadn't really expected to rear its head, not only do we see large changes in coordination in the aqueous environment, but also you see changes in the preferred spin state. So, and the energies involved are really quite dramatic. So in this case, it's cobalt, and we're going from high spin to low spin, depending on how we might along the transition pathway. This is the final results slide, and this is a kind of complex story that I just want to try and boil down. The vertical axis here shows the distance of the aluminium separation from the surface, the distance between the aluminium and the surface layer. So this is the external surface, and these are interior layers within the crystal. This is now actually a different composition to the sodium material that I showed you a while back. So this is actually proton compensated. This is one particular material called chabazite. These crosses here denote actually that water has been formed by the charge compensating proton combining with a silanol group on an SiOH species on the surface, and it's that liberation of water which gives rise to a strong driving force. What you can I've partitioned the data actually into these different types of sequences, which if you remember, I asked you to keep in mind a few slides back. So these are the types of sequences that we would expect, and it turns out that if we can compare the interior of the structure, interior and towards the surface, it's more favorable to form these, to push the aluminium towards the surface in these types of sequences. But you can see here that we've got a relative energy plot. Now, it turns out that it's actually much more favorable to form aluminium, oxygen, aluminium linkages when you have protons present as a charge compensating species. And it's much less discriminating about where the aluminium is, except for one particular configuration. Now, this points towards competing things going on in the structure. It's recently been reported that actually the silicon within these materials is actually quite dynamic in it, and contrary to popular opinion, it can easily come out of and go back into the structure, and hence we expect the same thing to happen with aluminium. So there's a layer of complexity, if you pardon the pun, to do with how the aluminium is distributed within these thin films of zeolite. So I'm going to finish there, but I need to acknowledge members of my group. So Ivan Clayson did the work that I've just talked about to do with aluminium segregation within zeolitic thin films, and also migration of transition metals. Dan Hewitt has done the high throughput work on zeolitic systems. Martin did that work on the IO66 with the rare event sampling, and Tom has been doing high throughput work on metal organic frameworks. I'd like to acknowledge some key collaborators, but also in particular the Royal Society, who funded an industry fellowship, which has allowed much of this work to happen. And I will finish there. I'd be pleased to take any questions. Thank you.
Okay, great. Thank you very much, Ben. So I think we probably have time for a quick question, if anyone would like to ask something.
Yeah, hi Ben, so it's Alex. Just wanted to ask about these frameworks. So if one kind of looks at these frameworks, then one can think, okay, so they should be easily twisted. Say, for example, these metal organic frameworks, because these organic things are, not very strong. But of course, yeah, twisting is very difficult to look at in a kind of mesoscale. But does it actually happen experimentally? That says because here they look kind of rigid, but if you
This
can,
is a
yeah.
Thank you for your question. So this is an atypical material, UIO66. So because it has this SEC type lattice, each of these clusters has got 12-fold connectivity. So they are indeed, this particular material is extremely rigid. And we, as mentioned, I can introduce a large number of defects, and actually it still preserves its topology. There are plenty of other frameworks which are actually rather dynamic in terms of pressure response or in terms of thermal response. So there's one particular material which actually will essentially double its volume as you approach room temperature. And there are some even more spectacular examples where the flexibility of the linkers is really important in allowing the structures to undergo very, very dramatic phase changes in the presence of guests.
Can I ask a question?
Please.
Okay, it's a little bit more general than what you were talking about. It is in terms of the growth of those systems. Usually people can grow very small single crystals of morphs, and they work with pellets and pressed pellets of different morphs for different applications. What do you know about a possibility to build really large single crystals of morphs, and particularly of those that are electronically conducting, like new interesting electrode materials?
I can't comment specifically about conducting MOS. That's certainly a super interesting area. I can direct you to a reference or some work by Jeff Ozim, published actually quite a long time ago, which was where they worked on, I believe, synthesizing very large crystals of metal organic frameworks. It's true that you can influence the size of these crystals quite dramatically, and there are people working on making monoliths of these materials. So possibly one of the key challenges actually with respect to electronic conduction is it's controlling defects. This is probably one of the big hazards in terms of the actual crystal engineering. I can't give you an example that I know off the top of my head where people have been able to generate super large crystals.
Because in order to have them, for instance, as electrodes, then you want to be them woolen filling and really be large, at least 10 micron thick, like that in normal direction. But so far, I haven't seen such systems. All people are working with pellets.
With respect to that, I mean, there's a paper that was published, I think, just last week, which was lithography of metal organic frameworks, which I can probably direct you to. Okay. Similarly, people have worked on using CVD to deposit layers of metal organic frameworks onto substrates.
If you can drop me a reference, it will be great. Thank you very much. Bye. Yeah.
Okay, thanks for your question.
Okay, thank you very much. So we are a little bit over time already. I also would have a couple of questions, but in the interest of time, I'm not asking them now. Maybe I drop you an email, Ben, later on.
Thank you.
So again, I would like to thank Andrew and Ben for giving two excellent talks today. And I would like to take this occasion also to announce the event next week. So there will be a highlight talk on yet another topic, which is biomolecular simulation of proteins by Max Planck director Helmut Grubmüller. So I very much would like to ensure you also to attend that meeting, online meeting next week. With this, I would like to hand over to Karen, who I think will sort of will basically exit this meeting in a sort of controlled way.
Thank you, Jochen and Ben and Andrew for the talks today. That's it really. Just keep an eye on the website, keep subscribing to the YouTube channel. We're uploading content every week, so it's once you're subscribed, it does actually, I'll put my camera on, it does actually notify you whenever we upload more content. So sign up for the newsletter if you haven't already, and we'll see you soon. Thanks everyone.
Bye-bye.
Bye.
Thank you.
Thank you.